minute.
Excellent. Well, I'm going to use my speaker's prerogative to show you a picture of the comet that I got on, well, early Monday morning from Girton. So, and this is just with a, you know, a normal 35mm type digital camera. So there's the comet. Anyway, and it should be visible tonight. Okay, the story of the birth and death of stars is the story of the origin of everything we see around us, except, of course, for the hydrogen in this glass of water. It's also the story of the battle of matter against the force of gravity. And despite gravity being so weak, it's a battle that gravity always wins with either a whimper or a bang. And so what is it that we have to explain? Well, on the left there, you see a slice of a rock, a carbonaceous chondrite that's older than any rock on Earth. And it was a meteorite created at the time the solar system was born, and it essentially contains all the elements in the proportions that we see on this diagram on the right-hand side. And you can see it's a logarithmic scale from hydrogen at the top, hydrogen and helium. It's a steady decline with increasing atomic weight, with various bumps and peaks dotted over it. And this is something that stellar evolution must set out to explain. Now, when we look up at the night sky, we see that it is full of stars, and we are taught that these stars are unchanging. It's only the planets that move and change in the skies. But if we were to come back in 100,000 years' time, we would see the pattern of constellations had completely changed, as all the stars near us, around us, that we see in the sky sweep around the center of our galaxy. And if we were to come back in 1,000,000 years, we'd see some stars had completely disappeared and other new stars had appeared. So, like all good stories, what we really need to do is to go back to the beginning. Well, not quite the beginning. We're not going back to zero. And just to explain this graph here, on the bottom axis, you see time. It's a sort of pseudo-logarithmic, 3 seconds, 3 minutes, 300,000 years, out to 14,000 million years. And up this axis, we see temperature, declining temperature. And the story of our universe is one of continual expansion and continual cooling. So we take up the story when the universe is a few seconds old and the temperature is about 10,000 million degrees. And for the next few minutes, we see hydrogen, protons essentially, being fused to form helium, as conditions are very similar to those in the center of a star today. And so nuclear fusion is taking place. But after about 3 minutes, the temperature has declined to a mere 1,000 million degrees, and those nuclear fusion reactions cease, and we end up with essentially the composition, the average composition of the universe we see today: 75% hydrogen, 25% helium by mass, and a smattering of lithium and beryllium. Now, the universe goes on expanding and cooling until the moment comes when it's about 300,000 years old, and the temperature has dropped to about 1,000 degrees. Now, at this point, the electrons that have been buzzing around on their own lose enough energy that they combine with the protons to form neutral hydrogen and with the helium nuclei to form neutral helium. So the gas, from being ionized plasma, turns into a neutral gas and becomes transparent to photons, because before that moment, photons were continually being scattered off the charged particles. So the universe becomes a neutral gas, the photons travel in straight lines, and we get our first optical image, as it were, electromagnetic rather, I should say, because this is now redshifted way into the microwave millimeter region. We get this first view of our universe. And I'm sure you're all familiar with this view, but the important thing about it today is that it has density fluctuations of about 1 part in 100,000, which we see here with the typical scale of about a degree. And it's these tiny density fluctuations that are responsible for all the structure we see in the universe today. And we think that they originated when the universe was very much smaller, 10 to the minus 44 seconds, where they correspond or were triggered by the quantum fluctuations. And it is these slight density fluctuations that are going to create structure. So they are drawing their fluctuations in the dark matter that are drawing baryons, drawing hydrogen and helium in towards them. Now, the universe, of course, continues expanding and continues cooling, and we enter what astronomers like to call the dark ages. Now, the dark ages are called dark ages because if we were in the universe at this stage, with our eyes, we would see nothing. Now, that doesn't mean there aren't an awful lot of photons around, but they've all been redshifted in the infrared, so our eyes would not see them. And as yet, there are no stars shining. But nevertheless, matter is collapsing towards these higher density points, and we are about to form the first stars. Well, we think were born when the universe was about 600 million years old. And we are pushing back our observations back further and further in time, optical observations, in an attempt to see these very first stars. Now, these very first stars are fundamentally different from any stars that are born thereafter because they were made essentially of pure hydrogen and helium. And the fact that there were no metals, no other elements, apart from a little bit of lithium, meant that the radiation could be transferred through their atmospheres more easily, and therefore they could accumulate into much bigger mass objects than is possible today. And their masses were perhaps up to 1,000 or more solar masses. 100 solar masses is the largest mass you can have for a star today. And we think that these stars, they would have lived very short lives, and incidentally, this is an artist's impression, before they ended in massive supernova explosions, and they would have, we think that they may have been left black holes that are the precursors of the black holes we see in the centers of galaxies today. But this is another very current topic of research, trying to decide when and how rapidly black holes managed to grow in the early universe. And so after the very first elements were created in those first supernovae, then the interstellar material was contaminated with those elements, and essentially stars that formed thereafter were very similar, broadly speaking, to stars that are born today. And that brings us to the present day, or the nearby universe. And here we see a wonderful example of a background galaxy silhouetting a foreground galaxy. And whereas you're used to seeing the familiar luminous spiral arms of a galaxy, where the galaxy lies in front of the background one, instead of luminous spiral arms, we see these dark lanes. And so when we see dark lanes in a galaxy like this, and let's just zoom in onto it there, what we now realize is that these dark lanes are not the absence of material, but the presence of the dust and gas, the building blocks of stars. And when we look along this spiral arm here, we see these regions of current star formation, made red by the red light from hydrogen alpha. And incidentally, the white haze that we see over the rest of the image is in fact the unresolved images of the 100,000 million stars that make up a typical galaxy. Now, what we'd like to do is look at one of these red areas in a little bit more detail And sadly, we can't do any better with this galaxy, with the Hubble Space Telescope. So we come back to our own galaxy. And here is the core of a giant molecular cloud. Called a giant molecular cloud, it extends way beyond the edges of this image because it's full of molecules and it's relatively cool. But the center of the cloud has been collapsing under gravity and stars have been born. And if you watch carefully, we will go from this old Schmidt survey image from the early 90s to an ESO image, more recent digital image of the same area of sky, and we see the interior, hollowed out interior of this dense molecular cloud, and we see the clusters of newborn stars. And their ultraviolet light is clearing away the debris, but you can see there are regions of higher density. And I want to just now, I'm sure you're all familiar with this wonderful image of the Eagle Nebula, and we see the gas. What we see here is gas drawing together. This feature is about a light year long, and it's collapsing under its own self-gravity. As it collapses, it's being irradiated by some of these bright, young, hot, newly born stars, and you can see streamers of ionized gas leaving the surface here. And presumably the radiation pressure will also assist this collapse. So this is unlike anything we're familiar with in our common environment, something, as it were, drawing together under its own gravity. And what we see when we look at the tip here are these blobs of much higher density material resisting the erosion, and these are typically solar-sized in their dimensions. And if we were to come back in, well, I don't know, a few thousand years, perhaps tens of thousands of years, instead of that cloud, we might see a new cluster of stars. I have to say that this cluster is a lot more massive than anything that will appear out of that particular cloud. So what I'd like you to imagine is that this is what the environment looked like where the sun was born 4,500 million years ago, and of course the meteorite that we were looking at just now. So you might say, well, if we were born in such a situation, why aren't we in a cluster of stars here today? And part of the answer to that is given by this simulation. And this is a simulation, comes from a group in St. Andrews, Ian Burnell, who used to be around the Institute. You might remember him, some of you. It's 1,000 solar mass cloud, about 1.5 light years in diameter, and it's going to collapse under gravity. And the video, which we'll repeat, runs for about 500,000 years. So let's get it going. Now, this is a turbulent cloud of gas, so it doesn't just all collapse down to one point. What we see, and we will see the first stars emerging very shortly, there's one at the bottom, is that the stars then have the average velocity of the material out of which they were born. So what's actually going on here? Well, the gas is drawing together under its own gravity. So the volume gets smaller, the pressure rises, the temperature rises. And this would normally halt the collapse, but thanks to the coupling of electromagnetic radiation to matter, we can radiate away that heat and cool the gas cloud. So the collapse can continue, and it continues. The smaller the object gets, the greater the force of gravity, the greater the ease of gravity to overcome the pressure. Eventually we get to the point where the temperature just goes on rising and rising, but gravity can beat the pressure at this point, and the temperature rises until it becomes hot enough to trigger the first nuclear fusion reactions, and then pressure generated by those nuclear reactions via the heating of the gas. The nuclear reactions heat the gas, raises the temperature, creates the pressure that resists gravity, and there we have our star. Now, what this simulation doesn't show you is that only about a quarter of the mass ends up in stars. The rest of the mass is blown away by the radiation pressure of the newborn stars. So although we had enough mass to collapse and gravitationally bind the collection, otherwise it wouldn't have collapsed, by the time we've made stars, we don't necessarily have sufficient gravity to retain the cluster. So a cluster of stars may be very temporary because the star's individual velocities can exceed the escape velocity of the cluster. So the cluster evaporates, and the other thing we have to remember is that since our sun was born, it and the stars born with it have orbited around the center of our galaxy about 20 times. So they're no longer, we will no longer find them associated. Now, if we were to look for our sun at this stage, we probably wouldn't see it because it would have been shrouded in the residual gas cloud out of which it was being made, and it would be, and then we would see a disk. This is a face-on disk around this particular object, an edge-on disk here, and another example of a disk forming around a newborn star. And these images are all about 1,000 light years away in the Orion Nebula. Now, this is the natural equilibrium configuration. You have a problem. You always have angular momentum in astronomy. It's everywhere. It's what shapes galaxies. It's what shapes accretion disks around black holes. And it's what gives us planets. And so the mechanics tells us that essentially we are giving up some of the angular momentum of the forming star. So the star can form a sphere in the middle. We give that angular momentum back to the disk. And when we look at our solar system, for example, we see that although 99.9% of the mass, give or take a bit, is in the sun, 99.9% of the angular momentum is in the orbital motion of the planets. And that is despite the fact that the sun itself is rotating. Now, with the ALMA telescope, it's possible to observe some disks in, this is in between 0.3 and 3.6 millimeters. The ALMA telescope in Chile has got this image of a disk almost face on, and we see gaps in this disk where we think planets or larger bodies are being formed. And this thing is probably no more than 1 million years old. And just to give you a sense of scale, I put the, you'll see this thing is very much bigger than our solar system. So what we are looking at largely out here may be the equivalent to the Kuiper belt asteroid belt, because there's Neptune's orbit and the Earth's orbit's right in the middle. So that's what it looks like at millimeter wavelengths. If we look at it in the optical, we see there's the disk, and that's within that box here. And we see a heavily obscured region, and we see evidence of other star formation and jets emerging from at right angles to these disks. And these things known as Herbig-Haro objects. Here's one in this, it looks like a javelin and held by a fist. There is a star being born here with a disk around it, and probably the same thing that we see with active galaxies, and intertwining magnetic fields coupled between the star and the disk get twisted, and channel material, maybe a light year or more up and above and below the object, and we see a shock front here. We see evidence for another object here. And one of the most spectacular images is this one, where there's a star being born in here and we get these two opposing jets called Herbig-Hara objects, extraordinarily well collimated. I remember being at a conference many years ago on supernovae, and one of the people from Los Alamos saying that if only we could achieve this degree of collimation with rocket engines, we would have an extremely efficient form of propulsion. So what is a star? Well, a star is mainly made of hydrogen and helium, and it's a sphere of gas in what we call hydrostatic equilibrium, where the force of gravity is exactly balanced by the outward pressure. And we can draw a sphere anywhere inside the star, and we can see the force of gravity at every point is exactly balanced by the pressure. And this is a very a stable equilibrium. What do I mean by that? I mean, if we were to pile more mass on, gravity would increase, it would squeeze the core, this would increase the pressure, and the rate of nuclear fusion reactions would increase and balance this out. If we were to scoop mass off, the pressure would drop due to gravity, and the resulting core would then expand a bit, cool, and the nuclear reactions would slow down. Now, this interior is very foggy, so the energy released here in the form of photons, high energy gamma rays, is slowly scattered. It makes its way up by a process of random walk, and the photons, ever being degraded by successive collisions, take maybe 100,000 years to get to the surface before they whiz off at the speed of light. So that's essentially what a star is. It's an extraordinary, if we were to strip off the outer layers and instantly reveal the nuclear fusion core, it would be about 3,000 million times brighter than the sun. So the sun is an extraordinarily good insulator in practice. And of course, it is this business of the nuclear fusion reaction is what stops gravity squeezing this sphere of gas all the way down to a black hole. Now, what is going on here, and what goes on in stars for most of their lives, is converting hydrogen into helium. And of course, eventually the helium gets used up, and we've already, the hydrogen gets used up, and we've already used quite a lot of the hydrogen in the core of the sun, and as a result, the sun is about 30% more luminous than it was when it was first born. And this is because the helium nucleus is more massive, so for a given pressure and temperature, we have a higher density in the core, and so the rate of the nuclear fusion reactions increases. So we might say, what happens when the hydrogen is used up? Now, we can explore that either with theoretical models, or we can move somewhere else in the universe and have a look at a globular cluster. This globular cluster is nearly as old as the universe itself, and about 3 times older than the sun. And so stars like the sun have already come or coming to the end of their lives. And if we look in detail, we will see these bright yellow-orange luminous stars, which are red giants, in contrast to the rather fainter and therefore lower mass main sequence stars. And the prime example of such a red giant is Betelgeuse up there in the top corner of Orion. So what is actually happening here? Well, hydrogen burning comes to an end in the core, so gravity squeezes the core contracts, and as the core contracts, the outer atmosphere of the star expands. And there are 2 ways of looking at this. One is that it satisfies sort of something called the virial equation, which balances kinetic energies of gas with the force of gravity. The other is to say that if we've got a certain amount of energy to get rid of, we can either radiate it away from a large cool object, or a small hot object. Yeah, and they'll get rid of the same amount of energy through the Planck law. And what governs the way radiation travels through the outer atmosphere of the star are things called the opacity, the fogginess, and this is governed by the metals and the free electrons from the ionized metals. So it's kind of the atmosphere structure gives us this situation. So the core heats up, and we have a shell of hydrogen burning, and eventually we have the helium core flash. The helium burning starts in the core. Now, the good news is that the sun will be nothing like as big as this red supergiant. See size of star here, size of Earth's orbit. Even Jupiter's orbit would be inside this object. And incidentally, this is an image from the Hubble Space Telescope. The bad news is that despite the sun not being this size, it will be big enough to swallow up the Earth. So in about 7,000 million years' time, the Earth will be turned back into gas and go back into the sun. Now, that may be the end of the Earth, but it's not the end of the story of the sun. The sun's outer atmosphere will, the red giant atmosphere, will expand and detach, and it will become a planetary nebula. And here we are seeing something about an Earth-sized core that is at a temperature of about 100,000 degrees, surrounded by an envelope that's maybe the order of a light year or more in diameter. And these things are referred to as planetary nebulae, not because they have anything to do with planets or even the swallowing up of planets, but because to the 19th century astronomers who couldn't easily resolve them, these glowing spherical balls, which some of them appear, were reminiscent of planets. They come in all kinds of shapes and sizes, and this one, and this one, and this one may be examples of the same sort of object, just seen from different aspects. And I'm just going to go through this lovely gallery of images of planetary nebulae, that is, objects, stars like the sun coming to the end of their lives. And the previous image and this image are of the same object. What's interesting about this image is these circular shells here are material that the star lost before it became a red giant. Maybe in its main sequence phase, the steady stellar wind was running at about 10 to 15 kilometers a second. Our sun has a stellar wind. And then at the end of the red giant phase, when the atmosphere detached, this material is traveling at more like 50 kilometers a second. And one of the mysteries about these objects is the extraordinary symmetries we see from one side to the other. And we suspect magnetic fields may have something to do with this. We always resort to magnetic fields. And we also believe that some of these will be maybe double systems, or they'll have residual disks around their equatorial regions, disks like the Kuiper asteroid belt, which will control the flow of material out from them. And these are just more examples of these beautiful objects. And this one is the Helix Nebula. I think it's about half the diameter of the full moon, and it's 700 light years away. And here again, we see the star in the middle, and we see here the high velocity gas moving past the lower pre-red giant branch, slow moving stellar wind, and you'll see these sort of comet-like features, higher pressure regions resisting that flow. Now this object has something to tell us. It looks like smoke crossing it, and smoke is a very good analogy because this material here is in fact made up of very small micron-sized particles that are typical of cigarette smoke-sized particles. And what we are seeing here is some of the material that has been made in this object being blasted out into space. There'll be some heavy elements here, but there'll be a lot of carbon, nitrogen, and oxygen. So when you look at this object, you are looking at one of the sorts of objects that created the elements that were present in the universe at the time that our sun and solar system were formed. And one of the things to remember is that the universe had been going for about 2/3 of its present age before the sun and solar system were formed. And so all the material in the planets and the surface of the sun was made in previous generations of stars, of which, when it comes to carbon and nitrogen and oxygen, this sort of object is a typical source. So if you are a romantic, you can indeed think of yourself as made of stardust. If you're more of a realist, then you are merely the nuclear waste of stellar evolution. So what comes next? Well, we go back to our cluster, we magnify a region like this, all these white main sequence stars, we then inflate them, overexpose them, and we can just see the very faint white dwarfs. And the irony is, of course, that these white dwarfs started life more massive than these appear bright main sequence stars because they've evolved through the red giant phase. Now, when stars are born, there are always far more low mass stars than there are high mass stars. High mass stars, more mass, greater the forces of gravity, greater their luminosity, shorter their lives. And here is an example of a 25 solar mass star that is ferociously burning its nuclear fuel. The radiation from the surface is sufficiently strong that it is actually blowing the surface layers of the star away, and you can get rid of almost the entire outer atmosphere of the star. Now, if we were to look inside one of these stars, we would see what we call the onion skin model of a star's nucleus. So on this quadrant, we have composition, and this quadrant, the actual fusion reactions. Let me just explain this. You'll see delta M over M. It says envelope 0.6, and that means these add up to 0.4. What it means is 0.6 of the mass, or 60% of the mass, is in the inert envelope, colored red here, and the remaining 40% is in the core. And we use this way of portraying the object because if we did it in a kilometer scale, although this is fairly symbolic, we would find that the outer atmosphere was enormous, the core was tiny, and the bit in the middle was even tinier. So we use mass fraction rather than kilometers. So there are no reactions going on in the outer atmosphere. It has the composition the star was made of. Then we get to a shell of hydrogen burning, creating helium. Then we go to helium burning, that is giving carbon and oxygen. And as we go deeper, we see ourselves going up the periodic table. And what you can see is that we are making successively heavier elements in successive shells as we go in towards the center of this object. When we get to the center here, we see silicon burning, silicon fusion. We talk about burning in astronomy. It's actually fusion, producing these iron peak, iron and nickel elements. Just note the axes, the top of the core, 10 million degrees, 10 kilograms per cubic meter. Quite understandable that, still quite a low mass. But here we are at 8,000 million degrees, and we're at 4 million kilograms per cubic meter. Now, when we start producing iron, well, I should say all these nuclear fusion reactions portrayed here release energy, but we run into a problem when we get to iron. And this is explained by this binding energy per nucleon diagram. And what it says, it shows you how much energy you release if you go from hydrogen to helium. You release that amount of, if you like, nuclear potential energy. And you will see that this curve flattens out, comes to a peak at iron, and then drops away to higher atomic weights, higher mass numbers. And you will have been familiar with this from your cultural history, if not from your physics, because you will know that the first nuclear weapons used uranium and split uranium or plutonium. And when you split, you go to lighter nuclei and you release, say, this amount of energy or whatever your products of splitting are. So they were fission bombs. There's fission. And then the next generation used deuterium or tritium and lithium and so on, and were fusion weapons. So nuclear burning, so a star derives its energy from successive fusions, but when we get to iron, we can neither get energy from fission or fusion. To get a very simple understanding of that, you know that protons and neutrons are made of quarks, and the quarks are bound together inside the proton and neutron by the strong force. And some of that strong force, which acts over a short distance, leaks out and enables the protons and neutrons to bind together in the nucleus. So the electromagnetic force doesn't overcome the strong force of binding protons together. So to begin with, the bigger the nucleus, the bigger the binding force. But as we get to bigger nuclei, the effects of the strong force start to die out. And when we get to very large nuclei, they become less and less tightly bound by the strong force, which accounts for this peak. So let us just quickly look at these nuclear fusion reactions and their timescales. Here we've got hydrogen burning through the proton-proton or the CNO, and you will see that the timescale for a 15 solar mass star is about 10 million years or so. So most of its life it spends, as all stars do, converting hydrogen into helium. Then we get the helium fusion reaction, lasts about 1 million years, and then carbon-carbon down to 300 years. And then when we're going to oxygen, making these elements, we're down to 6 months. When we get down to the silicon fusion, we're down to 2 days. Now, why do these rates, we're releasing proportionately less energy, as we saw. Why do these fusion rates go up and up? Because a lot of as we go down here, a lot of the energy is released in neutrinos, which come right straight out of the star and therefore cannot contribute to the pressure to resist the force of gravity. So they are, if you like, wasted energy escaping from the star and heading off into empty space. So we very rapidly, towards the end of a star's life, get to this crisis of generating an iron core. And what happens next? Well, no energy comes out of the iron core, so gravity takes over and starts to squeeze the core. There's no source of energy to resist that. So the temperature rises, gravity goes on squeezing, and we get to the point where the temperature becomes high enough that the gamma rays are energetic enough to dissociate the iron nuclei. And this is an endothermic reaction. It absorbs energy, which again speeds up the core collapse. And if you like, we reverse whatever it is, 10 million years of history of nuclear fusion. The iron nucleus dissociates into helium or alpha particles, helium nuclei, and some neutrons. The helium is then dissociated by the gamma rays to protons and neutrons. The protons combine with electrons to form more neutrons. More neutrinos escape, and in about 1/10 of a second, the core collapses from about the size of the Earth down to about 20 kilometers in diameter. So there it is, forming a neutron star. The neutron star forms, and then the outer layers of the star fall inwards towards this neutron star, The neutron star is very rigid, so there is a bounce, a shock wave then propagates its way out through the infalling material. And although I've shown it symbolically here, this is actually a full 3D hydrodynamical simulation of a 27 mass star, about 300 milliseconds after core collapse. And at this stage, this is right deep inside the star. It's about 600 kilometers in diameter. And for once, the neutrinos that are being released, this region is so dense, the neutrinos are being absorbed and creating these bubbles. They are dumping some of their energy into the expanding debris. We used to have a problem getting supernovae to run because the expansion just stopped. So we need some of that neutrino energy. And what we are seeing here, the red, it's actually entropy, but it corresponds to temperature. Totally dissociated, lots of free neutrons in here, and we have the heavier elements up here. And at this stage, in this expanding shock wave, we have a very rich neutron environment. We have very high temperatures. We have silicon, that is, the iron, of course, has all disappeared in the core. So we make more iron by silicon fusion, and we irradiate those iron nuclei with lots of neutrons that are rapidly absorbed, and then the neutrons decay to protons. And when you have an extra proton, you go one up, you go to the next element up in the periodic table. So we'll come back to that. So a lot of nuclear fusion is going on. Well, we are absorbing neutrons, rapid neutron capture. Just to give you an idea of the density of a neutron star, if we took Table Mountain, and those of you who have not seen Table Mountain, all you have to know is that it's a kilometer from the sea level to the top. If we compressed Table Mountain to the density of a neutron star, this is the size it would be, which is just another way of saying that most of all material, the rocks of Table Mountain, are mostly empty space, and the structure of the mountain is defined by the outer electrons, if you like, between adjacent atoms. But if we got rid of all the electrons and just reduced Table Mountain to nuclear material, this would be its size, 100 million tons per cubic centimeter. And it is quite fun. Gravity, as you know, is a very weak force, but surely there must be quite a lot of gravity from this object. And indeed, I would barely be able to keep my fingers open. The pull on my fingers would be about 22 kilograms, which is about the weight of some heavy aeroplane luggage. Okay, so there we have the shock wave going outwards. We have the silicon burning to produce iron group elements that then experience the neutron capture, building up our process elements beyond that in the periodic table. The shock travels outwards, and after a few hours breaks through to the surface, and the star becomes a supernova. And back in 1987, we had the opportunity to see such a supernova, the brightest one since the invention of the telescope. Suddenly this star lit up, and I should add that this image is large, not because of the explosion, just because the light is burning out, fogging the emulsion. Now, even though there's lots of light, it's worth realizing that in a supernova explosion, 99% of the energy comes out in neutrinos, leaving 1%. Of that 1%, not surprisingly, 99% of it is in kinetic energy. If you threw a hand grenade in the air, it would explode with a big flash, but most of the energy would be the fragments expanding. And that leaves 1% of 1%, or 10 to the 49 ergs, which can still outshine the light of a galaxy. After the explosion, 9 years later, we got to see the debris, and we saw that the star, there were 3 stars here. The star in the middle had disappeared. These 2 stars are not particularly close. They're nothing to do with what's going on. And we see this ring of material about 6 light months away from the origin of the explosion, and it is glowing, fluorescing under the ultraviolet light from the initial flash. We see a bit of expanding debris in the middle, and over the last, how can I say, 20 years or so, we have seen that ring of debris this ring of debris originated from an earlier stage in the life of the supernova in a kind of planetary nebula-like phase. And we see the ring of debris is being struck by the high velocity material moving at 9,000 kilometers a second. This thing starts to glow in the X-ray, it brightens up, and now it's starting to fade away as the material is dissipated by the expanding debris. And we can see how the debris was quite concentrated here, quite extended here. So what comes next? Well, the Crab Nebula is an example of a type 2 explosion about nearly 2,000 years ago, observed by the Chinese, and we see a mixture of material from the star mixing with the interstellar medium around it. And here's one that's about 11,000 years old, well mixed beyond that. Now, I'm conscious I'm running over my time very slightly, but I hope you'll forgive me here. There are a very few, fortunately, a very few very massive stars. And this is an example of one in the southern hemisphere. It's 100 solar masses. And that is the maximum mass that a star can have, because it's called the Eddington limit, Eddington luminosity. He worked out that if you have too much light coming from an object, the pressure, outgoing pressure of that radiation from that light, the radiation pressure, will exceed the inward force of gravity, and so the surface material will be blown away. And the upper limit is about 100 solar masses. 100 solar mass star is 1,000,000 times as luminous. So there it is. This is Eta Carina, and this is what Eta Carina looks like with the Hubble Space Telescope. And we see these two expanding fireballs dating back to a previous era in about 1820, when well, we're not quite sure what happened. We think that this might have been a triple system, and two of the stars merged in 1820, didn't create a supernova, but they did create this brightening. It became the brightest object in the southern hemisphere almost, and the expanding debris, which is now thinning. And in this image, you see where ultraviolet light is shining out from the star in the interior and illuminating by fluorescence some of the material that is in this space here, which is at a different temperature, so it doesn't show up other than through that fluorescence. Now, why are these things so important to us? Well, we have to jump back or forward to 1962, when there was a partial nuclear weapons testing ban, and it was agreed no more nuclear weapons would be tested in the Earth's atmosphere. And the Americans launched a series of military satellites to monitor the adherence to this ban. And they operated from 69 to 71. And they were sensitive. They were looking for gamma ray bursts. Now, a gamma ray burst takes place when you detonate a nuclear weapon. Now, they didn't see any on the Earth, but they did notice, well, about on average once a day, a gamma ray burst somewhere in the sky. And this catalog here they finally released their data in 73. This is a more recent catalog of gamma ray burst locations. And it's an all-sky image, so you will see that the objects are pretty uniformly distributed. And so we can immediately draw a conclusion that these objects are not associated with ordinary stars. because if they were, they would be all concentrated along the plane here, which is the plane of the Milky Way. They would look like the distribution of stars in the Milky Way, and they don't. So they're either very much closer to us or very much further away. And that mystery was solved in 1999 when a gamma ray burst was observed by a satellite that could also, I'm not sure whether it could or it had another satellite that could observe in the X-ray and tie down the location more accurately, which enabled it to be identified optically. And this is an image with the Hubble Space Telescope taken about 15 days later when it was about 250,000 times fainter. And what it revealed was some colliding, interacting galaxies at a distance of about 4,000 million light years. And what we think is happening here is that these are particularly, these massive stars, 100 solar mass stars, instead of forming a neutron star when they collapse, will collapse all the way to a black hole. And inside the collapsing star, the black hole will create an accretion disk. Material will be orbiting around the black hole, pouring into it, and probably again, as in active galaxies, it will generate collimated jets of material traveling close to the speed of light that punch their way out through the exploding star. When this high velocity material strikes circumstellar material, it will release gamma rays, and we see this pulse of gamma rays. So these things can be observed out to very, very far out in the universe, and Eta Carina is only 6,000 light years away. So we are mightily relieved that its axis of rotation, along which this jet would come, is not actually pointing at the Earth, because if it was, it might be rather disastrous for us. Now, I hope you'll forgive me if I go on. I think what am I going to do?
There's no problem with time, Robin.
What's that?
No problem with time.
Oh, okay, all right, yes, because we're not in a lecture theatre. Okay, well, up to now, I've been talking about single stars. And you're not expected to take all this in, but it's, it shows the outcome of different sorts of stars. We've got single stars, and then we've got double stars. Now, as you know, about half the stars in the sky are double. Now, we have focused on single stars, and we have shown that with the varying mass, low mass stars become white dwarfs, type 2 supernovae are slightly higher mass, you have neutron stars or black holes, and then the highest mass is these gamma ray bursts. Now, when it comes to double stars, we have all kinds of different phenomena here, and we don't have, we sadly don't have time to go into all of them, but I just want to give you the gist of what goes on. The thing about double stars is they're sufficiently close together that as they evolve, they can transfer material from one object to another. And the whole industry of astronomy is devoted to cataclysmic variables, where we have a companion star that is transferring material to a second star here, and the second star has an accretion disk. It might be a neutron star, it might be a black hole, might be a white dwarf. We have a hot spot where the material collides with the disk, and then we have all the phenomena associated with stuff in the disk. And of course, this thing is, it's a binary system, so it's in orbit. And this is how we put together the whole story, because as it orbits, different bits of the disk get eclipsed. And so by studying this thing photometrically and spectroscopically, we can put together, we can deduce the structure, because of course there's no way that we can see the structure. So broadly speaking, what happens? We have two stars, a high mass star and a low mass star, and this thing is called the Roche lobe, and it's an equipotential surface. And bottom line is this point here the pull, the gravitational pull of this star equals the pull of that star. So as this star becomes a red supergiant or red giant, if its size exceeds the Roche lobe, then material can pour over onto this star and alter its evolutionary history. So let's just take this example of a nova, a relatively not too high mass star, fills its Roche lobe, transfers some material over there, and becomes a white dwarf, and all's well. Eventually this star evolves, its low mass, so becomes a white dwarf later in its life. And eventually it fills its Roche lobe, and then it starts to transfer material back onto the surface of the white dwarf. Now, if the white dwarf is not too massive, then the surface, the hydrogen builds up on the surface until there's a runaway nuclear fusion reaction and we have a nova. And we think that all novae are recurrent novae. Some of them recur every 10 or 20 years. We suspect that many of them perhaps recur every 30,000 years. So the distinction between recurrent and non-recurrent is a bit superficial. Now, the story is the same, but if the white dwarf is close to the 1.4 Chandrasekhar limit, which is the limit of stability, when this object pours more material onto it, then instead of there just being a nova, there is a type 1a supernova. The whole star explodes or deflagrates it instantly, burns all the way from carbon or nitrogen or oxygen, all the way up to the iron peak elements, and in the process is completely disrupted, giving us a type 1a supernova explosion with no remnant left and heavy elements spread out into the atmosphere, into interstellar space. This is one that went off in 1006, and this is Tycho supernova, expanding at about 2,500 kilometers a second. Now, I very briefly want to mention one of the most exciting recent bits of work. There we've got our supernova type 1a down here. And I want to go down here where we're looking at much higher mass objects. And in this case, we have two high mass objects that successively become supernovae, and they leave a pair of neutron stars. Now, we've seen neutron stars orbiting each other for some years, but it's only recently that we have had the pleasure, thanks to gravitational wave detectors, of observing what happens when two neutron stars finally merge. And essentially what's happening here is they are orbiting around each other and emitting gravitational radiation. So they orbit closer and closer until they finally merge in what we call a kilonova. And here we have the gravitational signal of a kilonova from 2017, seen from two sites, but not from the third in Italy, which allowed us to pin down a location on the sky, the green bands here. And simultaneously with this merger, the Fermi satellite within 1.7 seconds saw a burst of gamma rays. And this was very exciting. There was its error bar, so we knew the thing was somewhere in here, not elsewhere. And this mobilized some 4,000 astronomers, perhaps a third of all the astronomers in the world. And they were able to track down this kilonova, which appeared in this particular galaxy. There it is. You can see it's already getting red. Kilonova are typically 1,000 times brighter than novae, but maybe 1/10 or 100th the brightness of a supernova. Although they are liberating far more gravitational potential energy, but most of that is being swallowed up in the resultant either neutron star or black hole. Now, the exciting thing about these was that when we observed them, we saw that the spectrum, and this is the very early day spectrum, 1.5 days, by 2.5 days, it had become highly reddened. All the blue light had disappeared, and that went on for the next few days. Some of the observations were made, and so the thing is very dim, and this is why it is so much dimmer. So what was going on? Right, well, I'm getting through this ASAP. This is what we think happens. When the neutron stars first emerge, there is a shell of ejecta. Now, neutron stars are not perfect, just balls of neutrons. They have an outer layer of heavier elements like iron peak elements and so on. So during this merger, there is an explosion, there is an ejecta that is full of iron peak elements and extremely rich in neutrons. So there is a very rapid neutron capture onto these iron peak elements, pushing the elements all the way up the periodic table. So that is going on there. The jet emerges, perhaps producing this cocoon on either side, and then the jet breakout, and we see the gamma ray burst. So this is the sequence of events. And the exciting thing was that the reddening of the supernova is caused not by interstellar absorption, it's caused by the fact that the elements, the lanthanides, which we will show in the periodic table, have many absorption lines in the blue part of the spectrum. So it's the newly created elements that are absorbing the outgoing radiation. So, okay, to finally summarize, we can say created in the Big Bang, forged inside stars, and then down here, all produced in rapid neutron capture. Some are forged by slow neutron capture inside these stars, some of these heavy elements, and the very heaviest produced by kilonova. So we can say the Big Bang, hydrogen and helium, mainly, Big Bang. Then we're dying low mass stars, that's red giants. We can see we produce what are called S-process elements, all the green things here, S-process by slow neutron capture, and carbon and nitrogen here. Exploding massive stars, the type 2 supernovae, we produce some iron peak elements and these other elements here, including oxygen from the type 2 supernovae. And then the type 1 supernova contributes quite a lot of the iron peak elements. Here you can see, and it's called exploding white dwarfs, and a few elements here. So you see for each element, the colors give you the proportions of that element that are made in that particular event. And then the exciting thing for the kilonova, the merging neutron stars, you will see way up the periodic table here, these gray things here are in fact unstable isotopes made in the lab. But you will in particular notice that just about all the gold that we have in the world was made in merging neutron stars. And I'm not sure why that's there twice, but okay. So I go to this, I'll just say this is the ecology of stellar evolution, high mass stars going rapidly around this way, low mass stars, far more of them going slowly around this way, ever enriching the interstellar clouds, not everything though being recycled, some of it ending up in the cosmic ash heap. In other words, inert brown dwarfs that will just float around in the galaxy for the rest of time, the cooling white dwarfs, the planets that aren't absorbed into the atmospheres like Jupiter and beyond will not be absorbed. And of course, on this side, the byproducts of the supernova, the neutron stars and the black holes that also end up in the cosmic ash heap. And you will see how particularly lots of heavy elements are generated by different sorts of supernovae. And one of the fun things to remember with a kilonova is that it relies on two neutron stars merging, and those neutron stars will have been produced in a supernova. So for every kilonova, there has to be a 2 supernovae, type 2 supernovae, that happened about a couple of 100 million years earlier. And very finally, despite the fact that we've been describing stellar evolution, even after 14,000 million years or so, still the universe is mainly hydrogen and helium. 0.8, this is of the 4% that isn't dark matter or dark energy. 0.8% is in stars. This is the mass energy. And only a tiny amount of the mass of the universe is in the form of elements beyond helium in the periodic table. And I think at that point, I will apologize for running on a bit, and I will stop sharing and